So the next video, now I'm going to discuss with one theorem on monotonic function. And what does it state? It states like this: a function which is 1 1 and continuous on a closed interval I is strictly monotonic. Strictly monotonic means either strictly increasing or strictly decreasing on that interval. Or we can say, in other words, if a function, if f is 1 1 and continuous on any closed interval, say I, then f is strictly monotonic, strictly decreasing or strictly increasing on that interval I. So let us see the proof here. You take, let A and B belong to I with A less than B. I here stands for the closed interval. Now what is given here? F is 1 1. Since f is 1 1, it implies that if f is 1 1 means distinct elements in that domain must have distinct images, implies that f of A cannot be equal to f of B. So therefore this implies that therefore either f of A is less than f of B or f of A is greater than f of B, because if it cannot be equal, then it means that either f of A is greater than f of B or f of A is less than f of B. So case 1 here, let us suppose here f of A is less than f of B. Now we shall show that f is strictly increasing. With fa of less than f of b, we shall show that f is strictly increasing. So here, A, as you can see, A, B here, A and B belong to I, and B here, A is less than B, which means that is B here is greater than A. It implies that f of B here is strictly greater than f of A. We assume here f of A is less than f of B, means that f of B is greater than f of A. So you name it as equation 1. So this implies that f is strictly increasing. With fa less than f of B, A less than B implies that f is strictly increasing. Now let us take, what we have to do is that we have to show that whatever points you take in this interval, in any open interval A and B, that this shows that for in that interval also f of x is strictly increasing. So let us take alpha here to be an element of this open interval AB, that is alpha here lies between A and B. And suppose if possible, f of alpha is less than f of A, with alpha greater than A, but suppose if possible f of alpha is greater than f of A, name it as equation 2. Now what we have to do is we have to consider a function, f defined by f of x is equal to f of x minus f of A. So clearly this f is continuous, because since f is continuous, since small f is continuous, so therefore this fx is also, it implies that capital F is also continuous on the same interval I. Now f of alpha, what is f of x? F of x, we define it to be f of x minus f of A. Now you replace x by alpha, what do we have? It is f of A minus, f of alpha minus f of A. But from equation 2, what is equation 2? Equation 2 is, we have assumed if possible f of alpha is less than f of A. F of alpha is less than f of A. It implies that f of alpha minus f of A is less than f of A minus f of A equal to 0, which implies that f of alpha minus f of A here, f of alpha minus f of A is less than 0. So this implies that capital F of alpha is less than 0. Hence, there exists point C lying between A and B such that f of C is equal to 0, because there is a theorem if f is continuous and if f of alpha here, if fa and f, oh sorry, I have to prove this one, there must exist, sorry, I have to show that for another point B. See, f of B, similarly f of B here, f of B is equal to f of B minus, you replace x by B now, f of A. And clearly we have assumed here by equation 1, what is equation? We have assumed f of B is greater than f of A. So using 1, f of B is greater than f of A implies that f of B minus f of A is greater than f of A minus f of A, which is called 0, implies that f of B minus f of A is greater than 0. So this is greater than 0 by using equation 1, whereas in this case we are using equation 2, using equation 1, whereas in the first case f of alpha, to prove that it is less than 0, we are using equation 2. So as you can see here, f of alpha and f of capital F, okay, f of B are of opposite signs, and f being a continuous function, it implies that there must exist a point C belong to open interval AB such that capital F of C is equal to 0. But what is f of C? That is f of C is equal minus f of A, because we have defined f of x equal to fx minus fa. You replace x by c here, so you will have f of C minus f of A is equal to 0, which implies that f of C here is equal to f of A. Now with A here, C belong to open interval AB, it means that C is greater than A but less than B. What does it implies? That f of C is equal distinct elements in A and C, they are distinct elements but they have the same image. What does it means? This contradicts the fact, which contradicts the hypothesis that f is 1, 1. So this contradicts the fact that f is 1, 1, because by definition of 1, 1, a function is said to be 1, 1 if distinct elements in that domain have distinct images. But as you have seen here, the statement of the theorem is that f is a 1, 1 function. Now we have distinct elements, A and C, they are two distinct elements, but they have the same image. This contradicts the fact that f is, and why that contradiction arises? Because we have assumed here, if possible, we have assumed this equation 2, if possible, f of alpha less than f of A. Because of this assumption, we get a contradiction. So hence, we must have f of alpha is greater than f of A. Similarly, we can show that f of alpha is less than f of B, because we have here, what is alpha? Alpha here, it is a point which lies between A and B. So if possible, first part, we have shown that if f of alpha is less than f of A, what we have proved is that f of alpha must be greater than f of A. Similarly, we can show that f of alpha also is less than f of B. So from here, what does we have? Does A less than alpha less than B implies that f of A is less than f of alpha less than f of B. From these two relation, it shows that with alpha lies between A and B, it implies that f of A is less than f of alpha less than f of B. That is f is strictly increasing on an interval I. So similarly, in the same way, in case 2 here, what is case 1 here? Case 1, we assume f of A is less than f of B, because either f of A is less than f of B or f of A is greater than f of B. First, case 1, I consider this. Now in case 2, you consider f of A is greater than f of B, with A less than with A less than B. Then in the same way, by assuming this, it can be proved that F is strictly, you can try this as homework, strictly decreasing. So in the same way as we have done in case 1, F it must be strictly decreasing. So hence, so this implies that by considering case 1 and case 2 implies that F is strictly monotonic. Strictly monotonic means it is either monotonic, it is either increasing or strictly increasing or strictly decreasing.